Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi everyone. In this video, I will talk about free charge dissipation in a conductor. So let's consider if we have one conductor. If the conductor is exposed to an external electric field intensity, so it will make the electron inside this conductor will be moved from one atom to another. So this condition will be make a current will be flowing inside this conductor with opposite direction, so compared to the direction of motion for the electron. So however, basically, even though the electron is moved from one atom to another, so normally actually we will have the value of electron and the proton inside this conductor is the same. In this particular case, so we will have a condition that we call it as a electrically neutral. So because of the number of electron and the number of the proton inside this conductor is the same, so we can have that our net volume density for the charge is equal to 0. So let's say we put another electron inside this conductor. So we will have excessive number of electron compared to the number of proton inside this particular conductor. What will happen? So first, basically the value of electric field intensity will be increased from 0 until certain value. So because we consider, so this is the conductor, this is a perfect conductor, so we can say that the early value for the electric field intensity inside this particular conductor is equal to 0. And due to excessive electron being put inside this conductor, it will make the value of electric field intensity inside this conductor will be rise into certain value. So because of the existence of external electron inside this particular conductor, so basically it will induce what we call it as a electrical force. And this electrical force, or Fe, will be produced or will be made the electron inside this particular conductor will be relocated, okay, from one point to another. So this condition will be continuing until equilibrium state reached, or what we call it as an electrical neutral will be reached again inside this particular conductor. So the charge equal to electron excessive charge, okay, will be accumulating at the surface of this conductor. So at that particular case, at that particular condition, so we will have the value of electric intensity inside this particular conductor will be reduced from the value here until to become 0 as it's originally stated. So however, how much that time need in order to make this equilibrium state reach? Okay, so let's consider equation that we have in the previous subchapter, which is continuity equation. So we will have del dot vector of j is equal to minus del rho v divided by del t. And by referring to the Ohm's law, whereas we have the vector of j is equal to sigma the vector of E, so if we replace this equation inside the first equation that I shown just now, so we will have sigma dot del dot vector of E is equal to minus del rho v divided by del t. So by referring to the first Maxwell equation, that we will have del dot vector of t is equal to rho v, and at the same time the relationship between the vector of d, electric flux density, and the electric field intensity is given by this expression. If we replace this vector of d with epsilon vector of E, then we will have del dot vector of E is equal to rho v divided by epsilon. So if we replace this expression, so inside the expression that we have just now, then we will have sigma divided by epsilon dot rho v plus del rho v divided by del t is equal to 0. So whereas at initial time, which is, or we call it as a t is equal to 0, so we will have rho v is equal to rho v naught. The general solution for this equation is given by this expression. So whereas we will have the rho Vt, okay, which is that the volume charge density is changed against the time, is equal to rho V naught exponential minus sigma divided by epsilon t. So let's introduce another time constant. So we call it as a relaxation time constant, whereas this time constant is equal to tau t is equal to epsilon divided by sigma. And if we replace this time constant inside this expression, then we will have rho Vt is equal to rho V naught exponent minus t divided by tau t, and the unit of it is equal to coulomb per meter cubic. So based on this expression, we can see that the rho V naught decay exponentially at the rate of tau t. So that's all for this subtopic. So should you have any question, so please do not hesitate to pass to me. Alright, so that's all. Thank you and good luck.